In this video, we're going to focus on nucleophilic addition reactions. So let's go over the generic mechanism. Let's say if we have a carbonyl group, in this case a ketone, and we're going to add a nucleophile to it. Typically, the nucleophile has a lone pair or negative charge, and it's attracted to the carbon that is bonded to the oxygen, since that carbon bears a partial positive charge. Oxygen bears a partial negative charge. So the nucleophile attacks the carbon, breaks the pi bond. And then you get this tetrahedral intermediate. Then in the next step, the oxygen with the negative charge grabs a hydrogen from H3O+. You can also use water too. And it turns into an alcohol. So this is the generic mechanism of a nucleophilic addition reaction. But let's work on some examples. Now let's start with cyclopentanol. And we're going to react it with a Grignard reagent. In this case, methyl magnesium bromide. In the second step, we're going to add H3O+. Go ahead and predict a product and also propose a mechanism to go from the reactant to the product. So based on the generic mechanism, we know that the double bond O is going to be reduced into an OH group. And we're going to add the nucleophile. In this case, the nucleophile is the methyl group. Magnesium bears a partial positive charge. Maybe not a partial positive charge, but it's actually a +2 ion, but it has a positive charge. Bromide has a -1 charge, which means methyl must be -1 as well. So the methyl group is nucleophilic, and it's going to attach this carbon. So this is going to be the product of the reaction. You could think of methyl magnesium bromide as being a combination of a methyl carbanion, a magnesium +2 ion, and a bromide ion. Just all connected together. It just helps you to see that this carbon is nucleophilic. It's the one that's going to attack the cyclopentanol. So now let's propose a mechanism for this process. In the first step, methyl magnesium bromide is going to react with the ketone. The methyl group attacks the carbon and breaks the pi bond. So right now we have an alkoxide ion. And we're going to add the CH3 to the compound. Now in the last step, the oxygen with the negative charge is going to grab a hydrogen from H3O+. Giving us the product. As you can see, the mechanism is fairly straightforward. There's not much to it. So that's how you can convert a ketone into an alcohol with the addition of an R group. So now it's your turn. Let's say if we have an aldehyde. Go ahead and predict a major product if we react it with the Grignard reagent, methyl magnesium bromide, followed by H3O+. And propose the mechanism as well. Feel free to pause the video. So to draw the major product, let's convert the carbonyl group into an OH group. And then all you got to do is add an R group to it. So we're going to add a CH3 group. And this hydrogen is still here. And so that's how you can draw the product of this reaction. As you can see, it's fairly straightforward. Now the mechanism is going to be the same. Just like before, the methyl group is going to attack the carbon atom in the carbonyl group. And then in the second step, the oxygen will be protonated by a hydrogen atom. So you can draw the hydronium molecule or the hydronium ion just like this if you want to. And so this is going to give us a secondary alcohol. Whenever you combine an aldehyde with a Grignard reagent, it produces a secondary alcohol. That is, of course, if the aldehyde has one R group. If you start with formaldehyde, you can make a primary alcohol. If you start with a ketone, you're going to get a tertiary alcohol. Now, using Grignard reagents is not the only way to reduce a ketone to an alcohol. You can also convert a ketone or an aldehyde into alcohol by the addition of a hydrogen atom, by means of a hydride ion more specifically. So let's say if we have 2-pentanone. We can turn this into an OH group using sodium borohydride, which is a reducing agent. The boron is attached to 4 hydrogen atoms, and so it bears a negative formal charge. Sodium has a positive charge. Now hydrogen is more electronegative than boron, so hydrogen bears a partial negative charge. Boron bears a partial positive charge, but the negative formal charge is not the same as the partial positive charge on boron. They're two different things. This nucleophilic hydride ion attacks the carbonyl-carbon, causing the pi bond to break, giving us an alkoxide ion. So the mechanism is very similar, but instead of adding a methyl group, we're going to add a hydrogen atom. And then in the next step, it can grab a hydrogen from H3O+, or we could use water as well. Let's use water in this example. And so this will give us a secondary alcohol. Lithium aluminum hydride works the same way. Sodium borohydride is used to reduce aldehydes, ketones. It could even reduce acid chlorides. But to reduce an ester, you need to use lithium aluminum hydride, LiAlH4. Now what's going to happen if we put an ester with lithium aluminum hydride? What products will be formed in this reaction? So in this case, aluminum has 4 hydrogens attached to it, just like borohydride. And the aluminum atom has a negative formal charge. So the hydride ion is going to attack the carbonyl-carbon, causing the pi bond to break. Now for aldehydes and ketones, we were able to add one R group, be it a methyl group from methyl magnesium bromide, or a hydride group from NaBH4. But with esters and acid chlorides, you can add 2 R groups. So this is what we're going to have after adding the first hydrogen. Now, at this point, the oxygen with a negative charge is going to use one of its lone pairs to form a double bond, expelling the OCH3 group. So the ester is reduced to an aldehyde. Now this molecule can react with an aldehyde further. Well, we should really call it an ion instead of a molecule. So another hydride ion will attack the aldehyde, reducing it to an alkoxide ion. So now we've added 2 hydrogen atoms. At this point, there's no other groups to kick out. It's very difficult to remove a hydrogen atom as a leaving group. It's easier to kick out an OCH3 group than a hydrogen atom. So the last step is to add either H3O+ or water to protonate the alkoxide ion and to generate the alcohol. So the product is ethanol. Methoxide is a side product. If we acidify the solution with H3O+, this can turn into methanol. Let's try this example. ET stands for ethyl, by the way. So that's equivalent to a CH2CH3 group. Now let's react the ester with methyl magnesium bromide. So go ahead and try this example. Predict the major product and propose the mechanism. So the methyl group is going to attack the carbonyl carbon. And so let's add the CH3 here. So we're going to have a tetrahedral intermediate just like before. And then this is going to collapse and kick out the ethoxide ion. So at this point, after the addition of one R group, we now have a ketone. But the reaction won't stop there. Another methyl magnesium molecule, methyl magnesium bromide molecule I should say, is going to attack the ketone and reduce it. And so at this point, we've added two R groups. So now the last thing we could do is acidify the solution with hydronium ions. And so this is going to give us a tertiary alcohol. And so this is the product. As you can see, the mechanism follows the same pattern, which is good. It makes it predictable. Now, what if we have an acid chloride? And let's react it with sodium borohydride. What will be the major product of this reaction? So go ahead and try that one. So this is going to work the same way. The BH4 ion is going to react with the carbonyl group. Now, acid chlorides are much more reactive than esters because chlorine is a better leaving group than the OCH3 methoxide group. So right now we have a tetrahedral intermediate. And here's the hydrogen that we added. So in this step, the chlorine's going to leave and we're going to have an aldehyde product for the moment. Now the aldehyde is fairly reactive, and so it's going to react with sodium borohydride again. So this substance is going to deliver another hydride ion. Reducing it all the way to the alkoxide ion. And then in the last step, it's going to grab a hydrogen from water. So in this case, we have a primary alcohol, 1-propanol. Now let's say if we want to convert an acid chloride or even an ester to an aldehyde, how can we do so? The reagent that we need is known as DIBAl. If you have an acid chloride and if you add DIBAl to it, this is only going to add one hydrogen. It doesn't reduce it all the way to the alcohol level. It's going to stop at the aldehyde level. Likewise, if you have an ester and if you add DIBAl to it, it's going to reduce the ester to an aldehyde. DIBAl is basically diisobutyl aluminum hydride. So you have an aluminum atom with only one hydrogen and two isobutyl groups, which looks like this. So this is DIBAl. Because it only has one hydrogen, it simply adds one and stops at the aldehyde level. But for this to work, the temperature has to be low. You want to carry it out at negative 78 degrees Celsius. Under those conditions, the tetrahedral intermediate is stable. So once you get to this part of the mechanism, let's say between an ester and DIBAl, this tetrahedral intermediate is stable at very low temperatures, at negative 78. If it's too high, this can happen. Now, before you get the aldehyde, you want to make sure all of the DIBAl has reacted. And so you want to keep the reaction at low temperature so that this doesn't turn into the aldehyde, so that the aldehyde doesn't get reduced by any leftover DIBAl. So once it stays in this form, you want to remove any remaining unreacted DIBAl molecules in the solution so it doesn't react with the aldehyde. Once you remove this, you can warm it up, and then the tetrahedral intermediate will collapse, turn into the aldehyde. And so that's how you can isolate the aldehyde in this reaction. So you want to keep the reaction at low temperature so it stops here, and then once you remove DIBAl from the solution, if there's any leftover amounts, then you warm it up, and then this will turn into the aldehyde, and that's how you can isolate it. Now what's going to happen if we combine a cyclic ester with sodium borohydride? What do you think is going to happen? In this case, if you add a reducing agent to a cyclic ester, which is also known as a lactone, the ring is going to open. Let's go over the mechanism for this process. So as always, the hydride ion is going to attack the carbonyl group. So right now this is what we have. Now let's show the hydrogen in yellow. Now this oxygen is going to use its lone pair, form a double bond, and break the bond. So once this bond breaks, the ring opens. So this oxygen now has a negative charge. And on the other side we have an aldehyde. Now the reaction won't stop here. Another BH4 minus ion can donate a hydride ion to attack this aldehyde, reducing it to an alkoxide ion. So now at this point, we can acidify the solution with H3O+. And so we're going to have a diol, a 4-carbon diol, which looks like this. So this is the product of the reaction. Now what if we have another lactone, but this time we're going to add a Grignard reagent to it. Let's use methyl magnesium bromide. So what's going to happen in this case? So this time the methyl group is going to attack. The ring is still going to open just like last time. So here's the CH3 group. And then the other oxygen is going to get kicked out. And so now instead of having an aldehyde on one side, we have a ketone. Now another methyl magnesium bromide molecule is going to reduce the ketone. You can't add H3O plus while you have the Grignard reagent in a solution. Otherwise, the CH3 can grab a hydrogen from H3O plus and turn into methane, which you don't want. So upon the addition of another methyl group, we're going to have a tertiary alkoxide ion, and we still have the other one. So now what we can do is add H3O plus. So this is going to grab a hydrogen. And so will this one too. And so we're going to have two alcohol groups. But let's redraw it. Let's draw it in a more different or a convenient way. Let's count the longest chain. Let's say this is carbon 1, 2, 3, 4, 5, 6. So let's draw 6 carbons. On carbon 1 we have an alcohol. And on carbon 5 we have another OH group. And there's also a methyl group on carbon 5. So this is the final answer for this reaction. Now, if we have phenyl magnesium bromide, what's going to happen if we react it with carbon dioxide? What do you think is going to happen in this reaction? Carbon dioxide can be drawn like this. It's a linear molecule, and the carbon has a partial positive charge. So the Grignard reagent is attracted to that carbon. So this is going to be the intermediate that we now have. This is known as benzoate. Now we still have the magnesium plus 2 ion and a bromide ion in the solution. So what you can do, if you want to, you can write it like this. But let's not worry about the Mg part. Once we add H3O plus, we're going to get benzoic acid. And so this is it. Now what's going to happen if we use phenyl magnesium bromide again? But this time we're going to react it with an epoxide followed by H3O plus. What's going to happen in this case? So the Grignard is going to attack one side of the epoxide. So we're going to add 2 carbon atoms to the benzene ring. And on the last carbon atom, we're going to have an oxygen with a negative charge. And then all we need to do is acidify the solution with the hydronium ion. And so this is going to give us a primary alcohol. Now, what is the major product between acetone and the cyanide ion? What's going to happen? Feel free to pause the video and predict the major product of this reaction. So the cyanide ion is going to behave as a nucleophile. This process is reversible, by the way. And it's going to add to the carbonyl carbon. And so we have this intermediate. Now this is how it's reversible. This can form a double bond, kicking out the CN group, given what we have back here. Now in the next step, this could react with another an HCN molecule, regenerating a cyanide. By the way, if this is in water, water can react with Cn minus to produce HCN. So these two are in equilibrium with each other, just so you know. So this oxygen can grab a hydrogen from hydrocyanic acid, regenerating cyanide. And so now we have a product that's called the Cyanohydrin, which looks like this. Now, what do you think is going to happen if we have an alpha beta unsaturated ketone? And if we react it with a Grignard reagent, and also let's use cyanide. What do you think is going to happen? The Grignard reagent is a very powerful nucleophile, so it's going to attack at the carbonyl carbon. The cyanide is a weak nucleophile. It's going to attack at the beta carbon. Relative to the ketone, this is the alpha carbon, this is the beta carbon. So the major product for the first reaction is going to look something like this. You're just going to get direct addition. And you've seen the mechanism for that process already. Now for the second reaction, the ketone will be unaffected, the double bond will disappear, and we're simply going to add a CN group to the beta carbon. But let's go over the mechanisms for both. So let's start with the first one. So the Grignard reagent is going to attack this carbon, causing the pi bond to break. And so here's the CH3 group. And then our last step is to grab a hydrogen from the solvent, which in this case is ethanol. And so we're going to have this product. Now for the other reaction, here's what's going to happen. So the cyanide molecule is going to attack the beta carbon. That's going to cause the double bond to move here, which will break this pi bond. And so here's the CN group. Now we also have HCN in the solution. So what's going to happen is this oxygen is going to form a double bond, causing this double bond to grab a hydrogen either from HCN or maybe from the solvent if you're using water too. And that's how the ketone will reappear. So we added a hydrogen here. And so this double bond is gone. And so that's the mechanism for conjugate addition compared to direct addition with the Grignard reagent. Now let's say if we have a ketone. What's going to happen if we react it with a primary amine and also a secondary amine? Now these reactions work well under mildly acidic conditions where the pH is around 4 to 5. So if you react it with a primary amine, you're going to get an imine, which looks like this. The imine has a double bond between a carbon atom and a nitrogen atom. Now if you use, let's say, a secondary amine where the nitrogen is attached to 2 carbon atoms, you can get the enamine product. In this case, there's going to be a single bond between the carbon and the nitrogen atom, but there's going to be a double bond here or on the other side. So this is the enamine, and the other product is called the imine product. So let's go over the mechanism for this one, but let's just use NH3, which will also produce an imine. So NH3 is going to behave as a nucleophile, and it's going to attack the carbonyl carbon. So let's say this reaction is carried out in water under mildly acidic conditions. So this oxygen now has a negative charge, and the nitrogen has a positive charge. Anytime nitrogen is attached to 4 atoms, it's going to bear a positive charge. So we can use water, which can act as a weak base and take away a hydrogen from nitrogen. When that happens, water is going to turn into H3O+. So now the solution is slightly more acidic than what it was before. So now the solvent can transfer a hydrogen to the oxygen. So now it's in the form of H3O+. So this is going to give us a carbonyl amine. Now what do you think is going to happen at this point? What's our next step? The next step is to protonate the alcohol. Let's use H3O+ to do that. Once you add a hydrogen to it, you're going to turn the OH from a bad leaving group to a good leaving group. So now this nitrogen can use this lone pair, form a double bond, and expel water. So now we have a protonated imine. So now we can use water as a weak base to remove the hydrogen. And so we have a final product, which is an imine. And so that's the mechanism for it. Now what about the enamine product? Let's propose a mechanism for that as well. So what do you think is the first thing that's going to happen in this example? So I'm going to draw the secondary amine like this. It's going to have an NH and 2 R groups. So just like before, the nitrogen is going to attack the carbonyl carbon. And so this oxygen is going to have a negative charge, and the nitrogen will have a positive charge. So at this point, we can either use water to grab a hydrogen from the nitrogen, or we can use water to transfer a hydrogen onto the oxygen. Now the solution is slightly acidic, so right now there's more hydronium ions than there are hydroxy ions. So now that we have water, let's use it to remove the hydrogen that's attached to the nitrogen. So now that water is back into its H3O plus form, let's transfer hydrogen onto the OH group. So as you can see, the steps are very similar. So this oxygen will take away hydrogen, and it's going to convert into a good leaving group. So now the nitrogen atom can use this lone pair to form a double bond and to expel H2O. So now we have an iminium ion. So notice that there's no hydrogen to take away from the nitrogen. And this is where the mechanism differs. Because these two are not hydrogen atoms, water is going to have to take the alpha hydrogen. And this is going to produce the enamine. So when water grabs this hydrogen, the carbon-hydrogen bond is going to break. Those electrons will be used to form a double bond, causing this pi bond to break. So now we have the enamine product. Another process that you need to be familiar with is known as reductive amination. So let's say if we have a ketone. First, let's add ammonia to it. This will convert it to an imine. Now, once you have an imine, you can add a reducing agent. Instead of using sodium borohydride, we're going to use sodium cyanohydrin. It works just like NaBH4, but it's a weaker version of NaBH4. This reaction, the conversion from the ketone to the imine, is reversible. NaBH4, if used, can reduce both the imine into an amine, and it can reduce the ketone into an alcohol. So because both of these exist in a solution, if you were to use sodium borohydride or even lithium aluminum hydride, you're going to get a mixture of products, 2-propanol and isopropylamine. Now, sodium cyanoborohydride is not strong enough to reduce the ketone. The electron withdrawn group, the cyanide group, weakens the hydride ions of the boron. However, it is strong enough to reduce the imine. So this will selectively produce the amine, which is what we want. So that's reductive amination, converting the carbonyl group into an imine and then reducing it into an amine. So let's propose a mechanism for the reduction of an imine into an amine. So let's see what we can do here. So this is going to be the reducing agent. And so just like all the other reactions, this is going to reduce the imine. Now this nitrogen with a negative charge has to bind to something. It could bind to the boron, which now has 3 bonds. And it could form an intermediate that looks like this. Now the sodium ion is still in the solution. When boron has 4 bonds, it still has a negative charge. Now once we acidify the solution, once we either add water or H3O+, then we can get the amine. So this bond will separate the nitrogen and the boron, and nitrogen can grab a hydrogen from H3O+, giving us the amine. Now if you want to keep it simple, if you don't want to show the reaction between the nitrogen and the boron, what you could do is simply add H3O+ to this part of the reaction. So once we had this intermediate, you can simply add water or H3O+. Let's use water. And this will also produce the amine.